Thank you very much for having me, and thanks for organizing this really great this workshop on a really great topic. And I'm so bummed that I have basically it's 8 a.m. in California, so I only caught a little bit of Bill's talk, and that's it. I really wish I would have been able to see all the rest, but I wanted to share some thoughts on what we might call value alignment in robotics, which is, I think, both a very functional problem and an ethical problem. And it goes something like this. So many times we formulate robotics problems as generating robot actions in service of some cost function, some reward function, some objective, some loss function, whatever you want to call it, some constraints maybe, right? Whatever you want to call it, formulate as like a search problem, an optimization problem, or some objective driven problem where there's an objective and the robot's job is to generate its actions autonomously in service of that objective. A lot of the work that we do in my lab is actually on how that problem changes when you have to interact with people, so that the robot is not the only agent that's there. It's not acting in isolation. It actually needs to be coordinating its actions with what people around do. And so we think about how robots can be generating their actions in coordination with the people in its environment, as well as in collaboration with the end user the robot is supposed to be assisting in the first place. And I have to admit that we deal a lot with people, but I know computer science and I know a little bit of robotics, and that's what I know. And so so somewhat embarrassingly, the lens through which we look at these problems is very much this robotics, the lens of robotics tools, right? So in order to generate actions around people, what do? Well, we squint until people start looking like robots, where they do planning and they do filtering and, they run Bayesian inferences. They do all these things that robots do. And if you model people that way, now, all of the tools make sense and gel well together and so on. And not that it's true, but it seems to have been a little bit useful from time to time in terms of enabling these robots to essentially work with people in manipulation, navigation, autonomous driving, and so on. But what I wanted to talk about today, and I'll get back to this lens somewhat ironically, but what I wanted to talk about today is what I found to be over the past, I'd say 3 or so years, 4 years maybe, to be a really major bottleneck in getting any kind of robot to do any kind of work around a person. And what some preliminary thoughts are on addressing this sort of fundamental roadblock. So it started, I really got the sense of just how bad this particular problem is when I started working on autonomous driving. So basically, I got to Berkeley and got into autonomous driving. And before our work, we were looking at sort of state of the art, and a lot of cars were optimizing for safety and efficiency. And that what was making cars really conservative. So it made them safe, which is great. We like safe cars, but it also made it such that, whenever there was a person in the target lane you wanted to merge into, you'd have to wait for that person to go and then merge behind them. And so if you want robots to merge in heavy traffic, good luck. If you want them to proceed through crowded intersections, good luck. Basically, people do the stuff and then you stay out of the way, and that's challenging. And so one thing that we've noticed is that we have to teach these robots a little bit about how their actions end up influencing the actions that people take. And so, this kind of typical, that's what I mean by getting robots to coordinate with people. You sort of do some modeling on the human side, you pretend like they're doing some planning, and all of a sudden you can account for the influence that robot actions have on the person. And then what happens is you get robots that know, there's a flip side. You get robots that know that they can, basically if they can gain a tiny bit in efficiency, they have no problem trying to cut you off and make you decelerate. So exert their influence on you, make you decelerate at 7 meters per second square. because it gains them just a little bit more in efficiency, and that's their, you know, efficiency was the thing that they are subject to safety constraints. Efficiency was what they are optimizing for. And so what do you do then? What you do is you realize, oh wait, there are other things that the robot should care about besides safety and efficiency. So, you know, we go back to the drawing board and we redefine the task specification, and we say, well, we want robots to be courteous too to other people, right? We don't want robots cutting other people off. We don't want cars that are jerks to human drivers. We need to add some sort of courtesy incentive in the objective. And we did that. And then it solved this problem, no longer robots cutting it off, but I think we did that a little too much. And so what happens is we encountered this four-way stop situation where the robot didn't go through. It didn't even stop there and let the person go through. It actually started inching backwards from the intersection, because that's the courteous thing to do. Because the way we define courtesy was by incentivizing the human's efficiency, and the robot, according to his model, figured out that if it inches backwards, it removes itself as kind of a threat from the person, and so that incentivizes the person to go faster to the intersection. So it's like this reverse influence, right? It was using before its influence to cut you off. Now it's using your influence to be super courteous and get you to go through. Now, this is weird. The problem with it is not that there's no issue with this person. This person that was going through the intersection was very happy with us. This is a new study. This actually worked, whatever. But if you have a car behind, or if you have a passenger in your car, now they're freaking out, thinking, why the heck is my car starting to go backwards at an intersection? And so you go again back to the drawing board, and you're like, okay, well, there's efficiency and there's safety constraints and there's courtesy, but there's also notions of passenger comfort, which I don't even know how to capture and write down mathematically. So basically, the point is that we build these optimization and reinforcement learning. There's a lot of progress in that. And it reduces the problem of generating good behavior to the problem of specifying a good cost function. And by a good cost function, I mean a cost function that when the robot uses to generate its behavior in every environment it sees, that behavior ends up what you want to see from the robot. And that is remarkably difficult to specify for these robots that interact with people. And it turns out, I find out, it doesn't even have to be for robots that interact with people. Take any sufficiently complex task, even if a robot needs to do it in isolation, it's really hard to specify what this task should be in this reliable way that will be bulletproof, no edge cases, nothing going wrong. An example of this that I really like came actually from OpenAI. So they did this work where they trained an agent via deep reinforcement learning to race in a boat racing game. So the agent, is over here in white, and did well in a variety of different situations, and then they encountered this situation. So this is what a trained agent did here. You might notice that it's not doing a good job racing. It's going the other way, first of all. That's a warning sign. And now it's doing this weird loop thing. And you might think, well, there's a bug in the policy, some deep RL gone wrong. It turns out, no, the boat is a genius. The boat figured out to do this loop and time it just right. And if it does that, it collects these turbo booster green things just as they appear. And each of them gives it like 1,000 points. And so the reward in the training was score in the game. The boat is doing a magnificent job at scoring the game. It's just not doing what we want it to do. We want it to race and win. But the boat is like, well, why bother, winning, racing? That's really hard. I can just do this loopity thing and be done. And this is not a new problem that I'm talking about. We know about this. We just don't really do much about it. So in the AI book, there's this example of a robot, a vacuum and cleaning robot. And Stuart and Peter say, look, imagine that you program this vacuum cleaning robot and you give it a reward, right? It's like you set it up in an MDP, you give it a reward. And the reward is you give it brownie points for the dust that it sucks in. Because you figure like the more dust it sucks in, the cleaner your floors are. So what is the optimal policy? The optimal policy, depending on the hardware you have, is to suck in a little bit of dust and then spit it back out and suck it in again and spit it back out and suck it in again, and do this repeatedly, because that's the quickest way to actually gain reward. And when I say it's a new problem, I really mean it. It's not even a problem in just robotics or just AI. It's a problem, you know, economics worries about this with something called the principal agent problem in terms of how do you structure your organization. We have myths and legends about this issue, that we should be careful what we wish for because we might just get it. That about our inability to correctly specify the thing that we actually want, the objective that we actually want. So there's this legend about, I don't know if it's a legend or it's something, I don't know the correct English word for what it is, some legend-like thing about King Midas. So King Midas wished that everything he touched would turn to gold. And his wish was granted. So you can imagine that he had a little robot assistant that said, your wish is my command. I will do what you asked me to do. I will make it so that everything you touch turns to gold. And it turns out, well, oops, that's not what I meant. What I meant is I want stuff to turn to gold, but not people, not food, right? I don't want my daughter to turn to gold if I hug her. So it's, you know, he got what he wanted, but not what he got what he wished for, but not what he actually wanted. So I think I know this is very long-winded to say this, but I just wanted to emphasize, I think, we worried about a lot about privacy and fairness and all of those very important things. But I think there's this kind of underlying thing that we often forget about, which is, what is this cost function? What is the objective for these systems that we plan or train or whatever it is what we're doing to generate their actions? And I think it's a functional problem, because you have to define some task specification that will reliably produce the behavior you want everywhere. So, it's a functional problem in the sense of, even without sort of adding any ethical issues, this is really hard to do. And then it's an ethical problem because you have to decide what you want these systems to actually be doing. And you have to be able to express that in code, in math, and whatever it is, right? So you have to take fairness and say, this is my definition of fairness. And sort of good luck with coming up with a definition of fairness that works reliably for every decision that the robot will ever have to make. So that's the issue. And for the rest of my time with you, I wanted to go quickly through the way we've started thinking about this problem and what we might be able to do about it. We do not have anywhere near an actual answer to this. I think I'd make a lot of money if I had an answer to this, but I just wanted to share with you a little bit of our thinking and sort of, one initial algorithm in this direction. So let's go back to this boat example, the boat racing game with the loop. What I worry about with this is, it's a toy problem, but it's representative of something that can happen. And in particular, what I worry about is not if this sort of thing happens during development time, where, you have an engineer that's testing the system. They notice, the boat is going in a loop. They would adjust the reward and fix it before they deploy it. That's fine. I'm not going to worry about that. I'm going to assume that engineers are doing a good job on development time at fixing the issues that they see. The problem becomes if you didn't catch this at development time and you're seeing this happen at deployment time. So you put a robot out there and you gave it a cost function, and now it's doing this behavior that's not what you want it to do. In the boat case, it looks something like this. The robot gets this new level, basically, where all of a sudden it has this opportunity yes, it has the same opportunity as before to win with a lot of points, say 20, but it also has this other opportunity to lose, but get a lot more points, say 50, or in the actual case, it was like 20,000. And it chooses the second. And that's a problem. Now, why does it choose the second? It's because you at development time told it that score in the game is the right thing to do. And so I think the thing to focus on is what happened at development time and how we might be able to fix it. So at development time, the reason you said score is a good idea is not because, you don't know how to write cost functions. You actually did probably a pretty good job. It's just that the levels that you were looking at are levels where the decisions, the options that the robot has look very different. At development time, you're looking at, well, I could either win with a lot of points, or if I don't get a lot of points, I'm also not winning, right? Score and winning are correlated at development time. And so score makes a lot of sense as a reward to specify. It actually works on all of those levels that the engineer tested it on. If you're hearing some chippity bird sound, it's my cat playing with its toy. Just wanted to add the little interference into our program. Okay, so back to the top. So score and winning are correlated at development time, but the problem is that there was some edge case environment that broke that correlation. And the person didn't think about that edge case, and we can't. We as people cannot think of every single edge case that will happen. Same thing for autonomous driving. You know, you see these situations where you put this influence in and the car actually does reasonable things in environments that you test, but in a particular configuration where you're sort of, you know, not quite behind the person, you decide that it's a good idea to go accelerate and cut them off. And this is this new, you know, it's a different kind of decision than the decision that you made because it's a new type of environment. It's just a different kind of situation. So long story short, I think what in general the problem is, I am the designer, I specify a cost function, I specify a cost function C tilde for the robot. The behavior that I want is incentivized by some other cost function C star. So you can think of C star as incentivizing good behavior everywhere. The problem is that when I write down what I think I want, it's not going to be identical to C star. It's going to be some C tilde that roughly resembles C star, but not necessarily identical to it, because I'm not a magic oracle and I can't just explicate, you know, here's the C star that will work everywhere. And so this is what happens, right? The designer has this, the engineer has this internal thing implicitly somehow in their head, and they can't explicate it. And it's ironic because I do a lot of human-robot interaction, and in human-robot interaction, we have people who have things that they want, goals, stuff like that, internal to them, and we don't ask them to write them down for the robot. We look at what they're doing, we interact with them, and we try to get the robot to figure out what they want and work with them to help them. And so, and I've done a lot of work in this area of trying to figure out what people's goals are so the robots can help them with it. But, you know, there I was as the designer with this goal, fuzzy goal in my head for what I want the robot to do. And for some reason, I think that I can just write that down because I'm an expert, I'm not a naive user. And therefore, I will just magically write this down and the robot will take it for granted and go off and optimize it everywhere and it will work out fine. I just don't think that that's the case. I don't think engineers are expert users. That's great. But I don't think that we can magically spew out in code or math the thing that we actually want. So the way I've started to think about the problem is that cost design or reward design is actually a human-robot interaction problem, just as much as interacting with the end users is. And robots aren't doing their fair share. They try to do their fair share with end users, but when it comes to the designer, there's no sense of an interaction that we're talking about. But I think there should be. I think there's a problem, a human-robot interaction problem that's just as or maybe more important than these other problems of actually collaborating with the expert to figure out what the right thing to actually optimize for is, to figure out what the task specification actually should be. And so kind of going back to this lens, I used to think about interaction from a robotics lens. And I kind of realized that I have to take this robotics problem, which is cost design, and really think about it from an interaction lens because people aren't magic oracles. And so really quickly, what this means is, you know, what does it mean to look at it from interaction lens? What does it mean for the robot to actually interact with me and help me figure out what it should do? One way we've been thinking about this is, through this lens that what I specify, the robot should understand that it's not ground truth, it's not C star. And instead, it's evidence about C star. I specified the C tilde, it shouldn't be taken literally, it's not the definition of C star, but it surely gives the robot some information about what I actually want is. And the question sort of became, how can the robot interpret this as evidence, right? What is the observation model for this? What's the problem? If I want C star internally and I don't even realize it, what comes out of my, developing the robot? What is the C tilde that comes out? What is this probability distribution of C tilde condition on C star? And so the way we started thinking about this is, if you look at cars and boats and whatnot, there's different things that go wrong at deployment time, but there's actually one thing that they have in common, which is that even though there's different aspects of edge cases and tasks going wrong, they're at development time, they're doing a good job. We're relying on this designer to actually do a good job specifying something that works not in general, but we expect that the C tilde that they specify actually works at the development time for the environments that they're actually looking at, for the environments that they're testing, right? We expect that the boat doesn't go in circles at development time, and we expect that the car doesn't cut people off at development time. And so we expect that at development time, the behavior is actually good behavior that comes out of optimizing this C tilde. And so that was our idea, that we shouldn't trust that the specified cost is the true cost, but we should trust that it incentivizes good behavior on those development environments. In other words, what we specify is not literal, it's contextual. It's contextualized by the things that we're looking at when we're specifying it, right? I'm not gonna come up with a magic cost out of no, I'm gonna look at some things and I'm gonna figure out what the cost should be such that the car or the boat does the correct things in those environments that I'm looking at. And so robots have to take that context into account when they interpret it, as opposed to interpret it literally. Mathematically, the way we do this is, this implies that the C tilde that I write down depends on C star, what I actually want, and it also depends on the environments, the development environments that I'm looking at when I'm designing this C tilde. And roughly, to take that insight and turn it into math, what it basically says is, if I look at the behavior incentivized by the specified cost, so if I look at these trajectories that come out of planning with a specified cost in the development environments, those have low cost with respect to C star. And that's the thing that I want, right? That I know about. And so that gives me evidence about C star. I know something about C star, which is on these development environments, those behaviors are good behaviors. And so to give you a sense, I don't know, geometrical, pictorially about what this means, it looks something like this. Imagine that I put on the x-axis all trajectories. It's an infinite dimensional space, but just to make it one-dimensional, these are all trajectories. And on the y-axis, I'm plotting the cost that each trajectory has in the development environment. And in green here, you see C star. I don't know what this is. I don't have access to this, right? But there's a cost function that corresponds to what I actually want. And, here it is plotted here. What this basically says is there might be other cost functions that you could define that will actually produce very different behavior. They see this one likes this one, here this one likes this. They actually do very different things. It trusts the designer to not specify this as the cost function because it just does not produce behavior that C star likes. But might be a lot of other cost functions that you can specify that actually end up producing behavior that's very similar to what C star actually likes. In other words, there might be many cost functions that produce good behavior in the development environment or environments. And we get into trouble when we specify one of these that's not C star, and when we move to a deployment environment where it's no longer the case that optimizing for the one I specified is also good with respect to C star. Their minima might be in totally different places. And so that's what we're trying to hedge against. And what this model is capturing is that if I specify one of these other green ones that's not C star, the robot is starting to understand that all of them are possible, that there's no way that I could have really disambiguated among them based on just what I've seen, because they all sort of produce very similar behavior at the development time. And so what this means kind of in our little toy problem is at the development time, I have these, possible behaviors that the robot could be doing. I mean, again, many actual trajectories, let's just boil them down to two. Let's say I can win with 20 points or I can lose with 1 point. And there might be a lot of different cost functions. And I specify score, I specify C2 maximizing score. That leads to the behavior and development time that wins with a high score. And now the robot sees that, and instead of just maximizing score all the time, what it does is it kind of takes a step back and says, okay, you told me to maximize score. This led to this behavior. Which other cost functions in my giant, I mean, in this case, there are 4 here for explanation purposes, but in my giant space of possible cost functions that you had access to, you chose C2, but what other ones are consistent with this? And so, of course, maximizing score is consistent with this behavior because it's the cost function that led to that behavior. Minimizing winning or minimizing score, notions like that could really blatantly contradict the score maximization. They're not consistent, but the robot realizes that this behavior, if you wanted to win, you would like this behavior as well. So it's not the behavior that you like just when you like to maximize score, it's also the behavior you like when you like to win. And so this is kind of going back, this is kind of, by just doing this inference, the robot is trusting some aspect of what you're saying, but not trusting everything that you're saying. So it's trusting you that, it shouldn't go ahead and minimize score, that's blatantly contradictory. It shouldn't try to lose, that's blatantly contradictory, but it's not trusting you that it could have really disambiguated between winning and score because those are actually correlated on this development environment. And so this does not tell us that you want to win. It doesn't, right? It just gives the robot this uncertainty over what you want. And it enables it to acknowledge that it doesn't know whether you want to win or whether you want it to have high score. And so it's a belief that the robot has. What it can do with this is it can plan an expectation. It can do risk-averse planning, sort of hedge its best against the sort of the worst case. And something that we're currently working on is it can go back to you and ask you questions to say, here's an environment where these things no longer correlate. Which one do you want? Like here, I'm actually, if I try to do what you said, which is optimized for score, there's this other thing that you could have meant that really suffers. Are you sure you didn't mean that? Because that's the kind of thing that we envision would happen. And that's what I mean by the interaction between the robot and the design. Just a quick example, we run this in motion planning because I do a lot of arm motion planning around people. And it's really hard to specify these cost functions because there's all these different things that you want the robot to sort of do, like stay away from people, stay away from objects, maybe in different ways. The person's head might matter a lot more than the person's shoulder and so on. So what you see here is 2 trajectories. The blue one is if you take my cost and optimize it in a new situation. And this is a cost that worked on a lot of different environments, but here's an edge case environment where somehow it decides that the right thing to do is knock through the base. Why? I have no idea. I don't know what changed about this environment. It doesn't look very different to me, but somehow in its decision space, it's different. And in orange, you see what happens if you plan an expectation. So the robot kind of hedges its bets more on the different costs you might have meant, and ends up maintaining safety. We also, with people, see that this leads to, it's easier to specify these reward functions. You end up doing it faster. You end up getting lower regret. There's also a lot of limitations with this. One of the things is that, where did C1 maximize winning come from? Like if the robot has access to that, it knows that that's a thing you could potentially want, then you can use our method to figure out, oh yeah, you might have meant that one instead. But where did winning come from? How does the robot have access to that as a cost function? This is something we've been thinking a lot about. We have a little bit of evidence that you could potentially run this sort of inference, not on, fully defined cost functions, but on fully defined features, but on actually the raw input features that the robot has access to. I'm going to skip some of that because I'm running out of time. But
I think you are actually 1 minute over time.
I don't even know. All of that. I'm just going to say that you can run it in the raw feature space. It does things like avoid lava that you've never seen, even though you don't know what lava is. So it seems kind of, it's doing something. The problem is, let me get to this slide. The problem is that when you do that, when you run on raw input space, you have to use these higher capacity models as a representation of the reward function. And the moment you do that, there's so many possible reward functions in your space that agree with the data that you've seen. And so the amount of data and the amount of interaction that you need for this really just blows up, and I don't know what to do about that. But again, I think cost design is a human-robot interaction problem. I think so far robots haven't realized this, and you know, we haven't made them do their share of the interaction. We just rely on us, the designers, to magically figure out the right definition for everything, and a cost function is actually reliable, and constraints that are reliable, and go ahead and deploy the robot. But I think it should be an interactive process. I think the robot should try to help us tease out what it is that we actually need. And with that, I'd like to thank you, and thanks for running this workshop, and thanks for inviting me.